Welcome back. In my previous video, I had seen about orthogonal vectors, orthonormal vectors, orthogonal basis, orthogonal complements of vectors. So I had seen any arbitrary vector x can be written as sum of two subspace W plus W par, where W par be the complement of this subspace. Also, I had seen any vector x of the vector space V can be made by sum of these two vectors xw plus xw par, where xw be the element of any subspace W and xw par be the complement of this subspace W, and any basis of vector can be written as basis of W union basis of W par, where W par be the orthogonal complement of the subspace W. Also, rho W union rho W par would be actually the orthogonal basis vector of the vector space V. I had seen in my earlier video any arbitrary vector actually made by this orthogonal subspace and orthogonal complement of this subspace. Are you getting? Well, and so I had seen orthogonal complement of M cross N matrix. I had seen for Rn the subspace are range space of A transpose and null space of A, and for Rm the subspace are range space of A and null space of A transpose. Also, I had seen null space of A is actually the orthogonal complement of row space of A transpose, and we all of us know complement is actually the whole space. So range space of A transpose is actually the null space of A complement. Similarly, I had seen the orthogonal complement of range space of A is actually the null space of A transpose, and if we apply complement again, then this would be null space of A transpose equal to range space of A. Okay. Also, I had seen dimension of range space of A transpose plus dimension of range space of A transpose par equal to actually the whole space Rn, because all of us know the orthogonal subspace and orthogonal complement of subspace equal to whole vector space. So, dimension of range space of A transpose is actually the rank of A transpose. So, rank of A transpose and dimension of complement of A transpose is actually the null space of A equal to N. So, by rank nullity theorem, we all of us know rank of A plus nullity of A equal to N. So, rank of A always equal to rank of A transpose. This is I had seen in my earlier video elaborately with picture. Today, obviously, I will see some basic property, and obviously today's video depends on only basic property, but this property is very important to understand whole inner product space in completely. At first, I will consider one inner product. Consider R2 with inner product U with V equal to x1 y1 minus x1 y2 plus x2 y1 plus 2x2 y2. Here U equal to the vector x1 x2 and V equal to y1 y2. Then the vectors 1 1 and 1 0 are orthogonal with respect to this inner product. Notice here inner product with this vector obviously 0. So obviously with this inner product, obviously this vector be orthogonal vector. But if we consider in R2 the standard inner product, then this vector not be orthogonal vector. That means from this concept I have achieved one idea. Every orthogonal vectors depends on with respect to inner product. Are you getting? I will say new expression. Today I will say some property of orthogonal matrix. And this is actually very important, this property, for any competitive exam. Properties of orthogonal matrix is a matrix with orthonormal column is denoted as Q. That means those matrices whose column are orthonormal is denoted as Q. And A square matrix with orthonormal column is called as orthogonal matrix. As for example, consider identity matrix. Here the column are orthonormal. Notice. So this is the orthogonal matrix. Similarly, the permutation matrix also orthogonal matrix. Rotation matrix also orthogonal matrix. That means in orthogonal matrix, actually those matrices whose each column be orthonormal. Okay. Now I will see some properties of orthogonal matrix. If Q is a matrix with orthonormal columns, then Q transpose Q equal to identity. Here the column is orthonormal. Q transpose Q means just this. Notice the idea. Q transpose Q means here n cross n matrix. Since each column be orthonormal, so obviously Q1 transpose Q1 equal to 1, and otherwise Q1 transpose Q2, Q1 transpose Qn all are 0. Similarly, here Q2 transpose Q2 would be 1 and other term would be 0. And if you continue this process, then this Qn transpose Qn would be 1. And this is actually nothing but identity matrix. Property, if Q is orthogonal, then Q transpose is equal to Q inverse. For orthogonal matrix, transpose and inverse always same. Third property, multiplication of a vector with the matrix Q, then this always preserves the length of a vector. That means multiply any vector x with the matrix Q. Here Q is the orthogonal matrix. Then norm of Qx square would be the length. And we all of us know norm of Qx square means Qx transpose Qx. And this is actually x transpose Qx. And since Q is a orthogonal matrix, obviously this is equal to identity. That means this is equal to x transpose x. And x transpose x equal to norm of x square. Therefore, multiplication of a vector with Q actually preserves the length of a vector. Notice? Well, it means when a vector with multiply by orthogonal matrix Q, then the length would be same. And when two vectors are multiplied with Q, then their dot product always remains same. The notation is such type QA transpose QB. Obviously this is A transpose QB. And since Q is an orthogonal matrix, then obviously Q transpose Q equal to identity. That means this is actually the A transpose B. That means when two vectors are multiplied with the matrix Q, then their dot product always same. And since dot product same, that means obviously angle between this vector always same. This property are actually very important for CSR net. In each year, there exists some question about this topic. So, I will highly recommend you, please see this video with pay attention, because this topic is actually very important for any competitive exam, not only actually CSR net. Now I will say some properties of orthonormal basis system. If a vector B is expressed as combination of orthonormal basis q1, q2 up to qn, then we can write B as x1 q1 plus x2 q2 up to xn qn. Then the coefficient of x1, x2, xn we can write as easily, just multiply this equation by q1 transpose. Then this would be, since this is scalar, just omit this, x1 times q1 transpose q1, then plus x2 times q1 transpose q2. Now omit this scalar also, then this would be xn times q1 transpose qn. And since q1, q2, qn are orthonormal basis, so obviously q1 transpose q2 would be 0. Similarly, q1 transpose qn would be 0. Only q1 transpose q1 would be 1. That means this value is actually x1. That means when I will multiply this equation by q1 transpose b, then I will get x1. That means the value of the scalar x1 is q1 transpose b. Similarly, the value of the scalar x2 would be q2 transpose b. That means the vector b can be expressed as q1 transpose b times q plus q2 transpose b times q up to qn transpose b times q. Means coefficient associated with each basis vector equal to projection of main vector on its basis. Are you getting the explanation? Oh well. Now I will see one nice result about orthogonality and linear independence. Consider V1, V2, Vn be orthogonal set of vectors in an inner product space V. If this is orthogonal set of vectors, then that implies this set be linearly independent set of vectors. And the proof is such type. Consider summation I equal to 1 to n ci vi equal to 0. Now consider one inner product with the vector v1. That means inner product summation I equal to 1 to n ci vi with v1, and this is equal to inner product 0 with v1, and obviously this is equal to 0. Then from this expression this is imply summation I equal to 1 to n inner product ci vi with v1 equal to 0. And since this is a scalar, ci is a scalar, so just omit ci from inner product, then this would be summation I equal to 1 to n ci with inner product vy with v1 equal to 0. And notice this part equal to non-zero when I equal to 1. Otherwise, all value would be 0. That means from this expression, this imply C1 with inner product V1, V1 equal to 0, because otherwise all term be 0. And from this expression, since this is non-zero, so obviously that imply C1 equal to 0. Similarly, if we apply inner product Ci Vi with V2, then I will get C2 equal to 0. That means actually I will get similar to before, C1 equal to 0, C2 equal to 0 up to Cn equal to 0. That means since all C1, C2, Cn equal to 0, that means obviously this vector V1, V2, Vn be linearly independent set of vectors. Are you getting? Oh well. Now I will discuss this concept by a picture. Notice the picture. Here the biggest circle be linearly independent. Then the orthogonal set. And notice orthogonal set always lies completely inside the linearly independent set. Then orthonormal set. Orthonormal set obviously lies between in this subset orthogonal set and linearly independent set. That means orthogonal set is a subset of linearly independent set and orthonormal set is a subset of orthogonal set and linearly independent set. That means from this picture it is clear orthonormal always imply orthogonal and orthogonal always imply linearly independent. But converse does not always true. If we collect all linearly independent set of a vector space, that does not always imply these vectors are orthogonal. Also that does not always imply these vectors are orthonormal. That means when the vectors are orthonormal or orthogonal, then obviously this vector linearly independent vector. Now I will see one basic example. Obviously this is basic but very conceptual. Consider the vector space V who is spanned by the vectors V1, V2 and V3. Notice the vector V1, V2 and V3. Then the question is obtain the basis and dimension of V and V bar. Notice here V2 and V3 are linearly independent. And this is linearly independent because V2 and V3 are orthogonal set. And notice V1 is equal to V2 minus V3. Notice if we subtract, then I will get this vector and this is actually the V1. So V1 is actually the linear combination of V2 and V3. That means the basis vector of the vector space V spanned by only V2 and V3. Because obviously these two vectors are linearly independent and they span whole vector space V. That means dimension of the vector space V is 2. Okay. Now I will see dimension of the complement of this vector space to find the basis of V bar. We all of us know V bar is the any vector which is actually orthogonal to any vector of the vector space V. So consider the V bar contain arbitrary vector ABC. Since this is orthogonal to every vector in the vector space V, so obviously this is orthogonal to the basis vector of V. So inner product Vp with V2 equal to 0 and inner product Vp with V3 equal to 0. Okay. Now put the value V2 and V3. Then by this relation A plus C equal to 0, that imply A equal to minus C, and minus 2B equal to 0, that imply B equal to 0. Therefore V bar contain the vector 1, 0, minus 1 and dimension of V bar is 1. Any vector space spanned by basis V and basis V bar. That means dimension of V plus dimension of V bar, which is equal to 2 plus 1 equal to 3. This is actually the R3. That means here the vector space is R3. This topic I had discussed in my previous video elaborately. I have just reviewed this topic again because this topic is very important for any competitive exam, and not only competitive exam, for higher study also. Okay? Let us know about the orthogonal basis. We all of us know the basis which is consisting the mutually orthogonal vectors. This is called the orthogonal basis. Since an orthogonal set, I have seen orthogonal set always imply linearly independent. So, an orthogonal set is a basis precisely when it is a maximal orthogonal set. That means there is no orthogonal set which is strictly containing this one. That means basis means this is actually orthogonal set of n vectors, but this is actually the maximal orthogonal set. As for example, consider in R2 this inner product. I have seen in my earlier video, this vector is orthogonal with respect to this inner product. That means obviously this vector is linearly independent, and this is actually the maximal orthogonal set in R2 with respect to this inner product. So, this vector is the basis of R2. Are you getting? When a orthogonal set be basis of the vector space? See, the orthogonal projection which I had discussed in my previous video. Just recall, because I have told you this topic is just basic part. Just recall, we all of us know orthogonal decomposition theorem. Just recall, given a subspace W of Rn and consider a arbitrary vector y in Rn which has a unique representation as the vector y as a written as y cap plus the vector z. The condition y cap be the member of the subspace W and z be the member of W part. We all of us know this is any vector in Rn can be written as y cap, which is member of the subspace W. This is the member of W part. That means the vector y project on the subspace W in the vector y cap. We all of us know this is, and also we all of us know this picture. So orthogonal projection theorem is, given a subspace W of Rn and any arbitrary vector y in Rn has a unique representation as the vector y equal to y cap plus the vector z, with the condition y cap belongs to the subspace W and the vector z belongs to W part. Then we call this y cap is the orthogonal projection of y onto the subspace W. We all of us know this is. And if u1, u2, un be the orthogonal basis vector for the subspace W, then orthogonal projection, which is actually denoted as y bar, is equal to y dotted with u1 over u1 dotted with u1 times u1 plus, this would be continue, plus y dotted with un over un dotted with un times un. Okay, this is actual formula to find orthogonal projection, where this vector u1, u2, un be the orthogonal basis vector of the subspace W. We all of us know. I had seen this part elaborately in my previous video. For example, consider the vector 2, 3, 4. Now let's say find the orthogonal projection of the vector y on the subspace W, where W is denoted as xy plane. Here, since W is denoted as xy plane, so obviously the basis of W is set of those vectors which contain 1, 0, 0 and 0, 1, 0. Then the orthogonal projection of the vector y would be by the formula 2, 3, 4 dotted with 1, 0, 0 over 1, 0, 0 dotted with 1, 0, 0 times 1, 0, 0 plus 2, 3, 4 dotted with 0, 1, 0 over 0, 1, 0 with 0, 1, 0 times 0, 1, 0. Are you getting the formula? Now calculate the value. Then this would be 2 over 1 if you calculate this times the vector 1, 0, 0, and this would be 3 over 1 times the vector 0, 1, 0. Then y cap would be the vector 2, 3, 0. And if you want to picture this vector 2, 3, 4, project on the xy plane 2, 3, 0. And this is the y cap, this is y, and this is the y perpendicular. That means y cap is the orthogonal projection of the vector y. Now let's see one more example. Here fx equal to 1 and gx equal to x. Then use the following inner product on the set C01 to find the orthogonal projection. Here the vector as a function onto the function g. Notice here the inner product is defined as integration 0 to 1 fx gx dx. This is very interesting. Here the projection of f onto g would be, the formula is inner product f with g over inner product g with g times g, and inner product f with g is actually integration 0 to 1 x dx, and inner product g with g actually integration 0 to 1 x square dx times g means x. Now after calculating the integration, this would be 3 over 2x. Are you getting? That means projection of f onto g is 3 over 2x, this function. Okay? I hope till now my all viewers will easily find orthogonal projection of any vectors. Today I will stop here. In my next video, I will discuss also other topic. But at first I will highly recommend you. Obviously today's video depends on a basic topic. But please see today's video with pay attention, because this topic is very important for deep concept. See you soon. Stay safe and stay positive always. Thank you so much.